Okay, let's get started. First, I apologize that uh, I have a little bit of my own health conditions, so I haven't got a chance to come up with another homework. Well, basically, is the principal component combined with discriminant analysis, the multi-dimensional separations. I just need time to type it down. And organize it in a fun way, and I'll get that done. The other thing is that I'll get your homework done, graded. Okay, I apologize. It's my own problem, but that's having said that, that shouldn't hurt too much for you to visualize where we're going. Okay, so we're basically trying to say that there are a lot of factors going to decide if you're going to play tennis or not play tennis by computer or not by computer for decision making. And I also said that so there are something good, something bad. So discriminant analysis or signal detection theory, generally speaking, can be used for optimization. Organize something in such a way that people will get into the good batch or buy computer batch or good customer batch. Okay, and so we're pretty much still trying to organize everything into that fashion. And to do that, I already said that there are two very simple way to do that. One is naive Bayesian. Naive Bayesian is I want something or I don't want something. Then there are a bunch of factor, good weather, bad weather, whatever, different kind of uncertainty. I treat them as equal opportunity. So multiply, multiply, multiply. And then at the end, you flip around and said that given uh, this condition, how likely I'm going to be in route A versus route B. And then probability high win. And end of the story. That is called uh, naive way of doing that. The other way I'm doing it is basically using a bunch of 2x2 table, build a choo-choo train, right? And then the choo-choo train just link them together, and then I fake the directions as long as I don't break the train. So I can fake the train from the top to the bottom, or flip around bottom to the top, or yank one and use that as the root cause, or the other way around, and then fake the directions. Okay, but that directions is what we're really looking for. And in order to do that, okay, there are directions very, very smart, and in such a way that once I ask something, I can make the computation quick. And also I can make the irrelevant stuff out of the picture. And to do that, we mentioned a couple tools last week. First, I talk about conditional independency or conditional independency. And that hint, okay, that example looks innocent, but it also carry a little bit more than just, hot and sour soup. I asked hot and sour soup questions. Once I asked, okay, do you like Chinese food? Inside that frame, and suddenly a bunch of stuff. We know that they're not supposed to be independent, but at least within the frame, it becomes independent. And what's the beauty of having a conditional independence? I can do a lot of computation without a marginalization. Oh, given this is the base, what is the under the subcategory? How many doing this? How many doing this? I don't need to flip upside down, sideways, because this is basically said within the frame. Look at inside the frame. If I have a smart frame, suddenly inside the frame, joint probability PAB given C become PA given C times PB given C. It's multiplication, and its multiplications log is summation, so the computation become really easy. So please put that as a critical note, is that the intelligence we're trying to establish in Bayesian network is try to avoid a lot of marginalizations of flip, summation equal to 1, and try to build a lot of conditional independency. Conditional independency is the intelligence of Bayesian network. And I hope the hot and sour soup example give you the mental picture really quick. And so if in a job interview, people say that, okay, I would like to build causal structure of something. Okay, what is the most important thing you would like to get out? So in other words, where is your knockout punch? I'll say the first thing is conditional independence. And then people say, why is this good? And you should have this hot and sour soup picture in mind and argue that because if I do it this way, inside the frame, things becomes easy. But to build this conditional independency, I'm gonna probably skip this for now, but I can come back. It's try to show you that you can tell there are a lot of computation. I can separate the computation very quickly, and then to reduce the unnecessary computation. And so we can do some accounting. This is very similar to those OR courses, talk about little o, big O, how many steps, that kind of argument. But there are proof, mathematical proof, but I won't do that because I feel that that doesn't give much uh, of your real world challenge. Okay, unless you get into a very OR PhD, I don't think you need that as much. But if I skip that, okay, for now, then what do I really? Where are we going? We basically said we need to build directions to build a structure. To build a structure, we need to find something to pull things out to make it easy. That pull things out in Bayesian network, the term is called D, A, B, C, D, D, D separation. Okay, and what's D separation? D means directional separations, and our job is try to figure a way to get to this. I think slide. I don't know if your number, but it's close to D separation. Slide 42. It's called directed separation. And then before that, slide 42 and the hot and sour soup part, I'll come back. This is just a bunch of evidence to show you that, hey, we can do this piecemeal, multiplication, one cell at a time. It's almost like doing the mutual information computation. And also, you guys did the Venn diagram for 3 circle cases. It's exhaust is a lot of work. So this is just to prove that computationally we can get those things done, quick way and not so quick way. And so it's important to know that's the benefit, but we're not going there for now because I want you to have a big picture, and so you can start playing with your own data. So the things what we want is to build a D-separation, or Julia Pearl called directed separation. And this is a quote from his books, okay? And it's roughly speaking, 2 nodes are deconnected if there is a causal path between them. And there's evidence that render the 2 nodes correlated with each other. So in experimental design, this is confounding, right? something they are related, but because there's a common cause, or if I can figure out that how one influences the other, but there is a common effect I can measure, then I can take that part out, and the rest is uh, you know once I take that common pieces out, I make the whole things it's what is that common piece, the confounding piece, the hot and sour, the Chinese food piece. That's the whole idea. Okay, and D separation is a property of two nodes. Okay, and respect to a set of nodes E. Okay, and I will let you read those things yourself. English in this kind of logical way is beautiful, but tongue twisting. Okay, so what we're really trying to say is that we try to build graphical model. Okay, marginal independence. Okay, if something, there's no connections, that means tossing a die, flipping a coin, it's purely independent. So how to have a 1 out of 6 head and some uh, random event, they're all independent, just multiply them together. Okay, and then when this has happened, is A causing A and causing B and causing C. Okay, so in this case is, if I know how to figure out a joint probability of ABC, all I really need to know is, given PA, the root, and then if A happen, how likely C happen, how likely B happen. So the joint probability become this expression. And how to verify they are follow this shape. You have a bunch of actual ABC, A1, B1, C1 until your factorial design, like your experimental design, and then you can count, right, using Excel, how many times this happened in actual, and here is based on this model, given A, and then given A to C, given A to B, then you can multiply them, you get your model probability, then you have two sets of probability under every conditions. Are they the same things or not the same thing? How to measure how close KO divergence, and then end of the story. So if I connect the dots this way, okay, give you just 10 seconds, sums up, you can connect them.
So to kind of recount
Mhm.
for a second, A would be your that conditional would be the key to your conditional independency.
Here, you're right, but I would like to say this. Okay, so you will have a probability table of PA. Okay, and then here it will be how many A event, A1, A2, A3 under different condition. What's the probability? And then you can have another table is A given C. Okay, buying computer rich, buying computer not rich, buying, and then so you can have a bunch of A conditions, and you can have bunch of A conditions numbers. Of course, the sum should equal to 1. And you can have a bunch of AC, PAC. Again, I don't know how many different A given C. You can arrange them in a 2 by 2, 3 by 3, but you can exhaust them as a column. And if you exhaust them in like a column, you can calculate a bunch of yada yada AC conditions. Agree? And then the sum also equal to 1. Agree? And then I can have a bunch of B, C, and then same thing. P, B given C. Okay, and then let me just fake this is a lot longer. Okay, but basically every A is exhausted in this probability table, marginal table. This is conditional table. This is a conditional table. We don't know it's true or not. But let me just say that I have a, this is true. This is what really happened. So now you have different A, B, C conditions in the real world under different, some things, under different ABC join. And so let me just say that different ABC join, okay? And then I'll call, I'll put it up here. I'll call this actual. So this actual is a bunch of ABC 2 by 2 by 3, I don't know, by anyway, a bunch of combinatorics. And then you will have a bunch of combinatorics. Under the conditions, I can do a tally. So far, so good. But then suddenly I'll have a model. And this model so far is science fiction. I'm just saying that here is the right model. Okay? This model is P A given C times PB given C and P, oh, I got it wrong, huh? This should be PC then, because C is the base. So this is, oh, PC. Okay, this is a model. This is called model 1. And since you have all this stuff, you can calculate them one by one, agree? And so here, once I calculate them one by one, I can compare the two and say, is this science fiction good enough to explain this? Actual. Kind of divergent. So far, so good. And then let's just say Grumpy Simon said, hey, I don't like that. I have a model 2. And a model 2 is PABC really equal to PC given B, P BC given A, and PA. This is my model. A causing B, B, and I'm not saying this is right. This is just another science fiction. How many science fiction I can build? Well, as many as you want. But then when I finished my science fictions, I said, based on this computations, I will have some value calculated, right? So now your model 1 is better or your model 2 is better? KO divergence, who is closer to the truth? So, so far so good. So number 1 criteria is at the end, you should, in your term projects, you should have more than one plausible model. And then you compare them one by one. That's step 1. The other thing is the principal parsimony, KO divergence, Occam's razor. If my model require 10 steps of computations, 3 table, and your require 15 computation and tons of tables, but at the end, your improvement of the KO divergence, the information gain, it's not much. Then we have a trade-off to determine over there, and you know you can use some Pareto principle and some argument to say which one. And a lot of time, guess what's the case? Who paying it? Who has the final say? Your boss say that I like that better, and that could be the case. So, having said that, I hope you have a pretty reasonable visualization where we're going. We just I'm a human factor guy, okay? So another thing I would tell you is that usually I don't like to build more than 7 or 8 model. Once is bigger than that, uh, you know, a lot of time uh, I feel very uncomfortable because uh, if I cannot explain it, I cannot generalize it. If I cannot generalize it, I cannot use it again. Okay. Now, so where we're going right now is we're trying to say that how to build those structure. So we can have common cause, common effect, and we can have the so-called Markov dependency. And this term, you have Markov chain, right? And what's Markov chain means?
It's essentially a continuous link between different nodes, which will give you conditional independence. Like so, B is dependent on A, just like C. It's semi.
Markov chain. Markov means that the previous everything I need to know, all the information I need to know about uh, where I am, it's carried by the previous steps. So the drunk walking, random walk is the example. I don't care where you're from, but in order to reach here, your previous steps must be one tile before. So every time you can push one step forward. So everything's you need to know can be carried by everything's before. And then, of course, everything you need to know of given A to B, B to B, C. This is so Markov dependency carry one thing is called the chain rule. And I think this is the example that I love to tell you where we're going at the end. So what we're gonna do is this, okay? Here, look at here. A cos C, A cos D, B cos D. So this is the disease. And if you have this disease, you have this side effect, you have this symptom. And if you have certain treatment, it will give you some ground improvement here. So can you see that everything is down arrow, down arrow, down arrow, down arrow here? So to have D happen, I know what? I know everything I need to know to reach D, I need to know A, B, C. Agree? And then on the other hand, if I want to know what will happen to my G or what will happen to my F, do I really need to know A, B, C if I know D? No, because of the Markov conditions. A, B, C, let me define. Hey, you have the disease, the injury, the low back pain, the carpal tunnel syndrome. As such, you need to wear back brace. You need to carry certain painkiller, or you need to have certain chair accommodations. But all those things is necessary if D is true. So uh, one course, I supposed to offer this semester and got canceled because is if I'm trying to build a dynamic graph, can you see that this graph actually right now is arrow down, arrow down, arrow down, right? can I turn these things 180 degree? And what's the beauty of turning everything 100 degree? I can say that if I have this time of treatment, I have this kind of side effect, and this, I probably will have this disease. And if I have this kind of disease, I probably have this kind of root cause or certain things. So you're basically treating a dynamic programming upside down. And this is actually, if you learn OR, dynamic programming or reinforcement learning, they talk about this is I can look at a world, okay, it's like a flight plan. Lift off or take off, reaching the cruising altitude, cruise, approach to the target area, and prepare for landing and touchdown. And so the Bellman equation basically said that if this is good, every step need to be in the optimum. So you will have the final. And sometimes when you try to evaluate this whole things or machine learn this whole things, you can flip around and say that I don't want to start from the beginning, origin to the target. I can say, this is what I want. I dream when I reach 65, when I reach 70, I should have this kind of, saving, this kind of health, this kind of something, so I can reach the final. So you use the final, you push back. In order to do this, then you must, in order to be here, okay, you need to at least approaching to the airport, the target airport or target area by this time. And in order to reach the target area by this time, you need to at least overcome the space and time barrier this much. And I will tell you this, okay, if you guys are interested in military history, read the Normandy invasions or major military operations. A lot of time they did this what they call SEMplay simulation, because at that time there's no computer. They did it back and forth the same way. Okay, we start from here. Okay, D-Day in step 1, step 2, step 3, and then sometimes push back. And everything's need to be right in order to be right. So one is called pushing forward, one is pushing backward. And sometimes actually people do it the third way. The third way is that I know there is a midpoint. It's a point I cannot avoid for psycho-social political reason. I need to be there. Or in order to, for example, so far so good. Treating everything upside down is reasonable, right? So Markov condition is trying to figure that out. Sometimes you can have a midpoint. And you just said that this midpoint is the point of no return. This point is the point of if you, NASA doing the countdown, or they prepare. They just said that this is a point of no return. And the military operation, same things. There will be a point of no return. Once you reach that point, that's it. So no alternative airport, like crossing certain dangerous area. And then they just use that point and said that, so how many way I can reach the midpoint? And then they use the target pushing back and look at things this way. So causal structure can be used for design. Causal structure can be used for planning. But in order to do that, is divide and conquer, try to make everything as small as possible, right? And how to make things as small as possible using de-separation, ask the right questions. So the first steps, let's do a checklist. First thing, would you agree with me? Computationally, any 3 nodes, you can be independent, common cause, common effects, or choo-choo train. Okay? So that is acceptable. Second things, would you agree with me no matter how big a complex structure, it would be nice to say that cause, that's definition, decisions, and then effect. And if we can summarize some note that way, it will be easy to look at the world a lot easier. Third thing, once you have the whole things become a flow of thinking, you can actually turn the logic 180 degree, cause become effect, effect become cause. Make sense? And so if you think that way, okay, uh, this table still the foundation. Mutual information still the foundation. KO divergence still the holy grail you try uh, to have. Okay, now let's do the names. Okay, in this, okay, in the D separations, okay, I have a choo-choo train like this. U, let me make U red. W red. Okay. If U and W red, you can see is this. V and X causing the common effect U. V and Y causing the common effect W. And then V is the common cause of U and W. So far, so good. As such, let's have our first hot and sour soup. X and V can be conditional about X and V are unconditionally independent because X, I don't know what causing X, and V, I don't know what causing V because there's nothing I can trace. Okay, so X and V are unconditionally independent. However, X and V are unconditional independent. The minute I said, hey, X and V, they have a common kid called U. The minute, and U is U's behavior depends on X and V. And now, so if I watching you, okay, conditional on, oh, you done this. If you done this, then X must be in some state and V must be in some state. So X and V become dependent, conditional on you. So if I cannot watch you, X and V, I don't know where you're coming from. I don't know where you're going. You look random, right? But X and V become dependent if there's a condition of you. So I'll give you a simple example. Dr. Dickey in statistics in NC State used to be my office mate. His paper, I want to show off, not me. Well, let me just use this. Yeah, should be. Let me try one more. David Dickey. Yeah, okay. You can read his Wikipedia version, and this guy's published tons and tons of paper. And if you look his H-index citation, uh, I don't know. He got one paper. It's called Dickey-Fuller test. Okay, This is widely used by Nobel laureate and is a highly cited paper. And why I'm talking about him, this Dickey citation or Dickey Fuller test is talking about uh, you know, stock market or any random event. You will see them kind of like they wobble all over the place, but at the same time, it's kind of like they're never really far apart. They're kind of like they still trace each other. So when I first met him, I said, Dr. Dickey, uh, when you done this, is it like you're looking at two ship or two boat chain with something? He said, no, that's not the way to describe this vividly. He said, you can consider this as a young lady or a little girl walking a dog, a big dog with a bungee chain. So a lot of time the dogs try to wandering around, and the young girl got certain walk she would like to follow. They cannot control each other completely. So a lot of time you don't know is the lady walking the dog or the dog walking the lady. However, if I can tell you I have some marker on the chain and I can trace the chain, if I know where's the chain, the girl is not going to be too far behind and dog's not going to be too far behind. So in other words, X and V are not really related if you don't know you.
So you would essentially be the elastic relationship between X and V.
I don't know. Well, in our world, is there's X can cause you, V and can cause you. Well, for example, would you agree with me that we're the product of our parents? So can X can be my dad, V can be my mom, and U is it's me. So a lot of time I don't really know what is the perspective of my dad or what is the perspective of my mom. But if I elaborate my perspective, I probably can trace back and figure out how X and U inter. So here is the part. Be careful here. That's why I said at the beginning, unconditionally independent XMV. At the beginning, if I that's the only two columns of data. I look at their correlation coefficient. There's nothing. But if I create a third one, U is a regression of X and V. And then now if I build those 2x2, 3x2, 3 table, I can tell the mutual, well, if I said U is a regression of X and V. So when I build a 2x2, 3x2 table, would there be any information gain or mutual information between X and V? Would there be any information between U and V? Yes. But then if I can partition out, take the part of the U out and said, hey, this part is what I took from X and V. And the minute I took those mutual information out, suddenly X and V from independent become dependent. They dependent is not because U and V, you can visualize this now, right? Yeah. So same thing. So what we're trying to say is that X times V, PX and PV originally is this. So if I calculate their mutual information is zero or close to zero. But then the minute I let them conditional on this, it's not zero. So I can do a bunch of data and then make that happen. Next, same theory here on this side. V and Y, they're not related. But the minute I get W involved, then uh, they are conditionally independent given U and hold on, hold on. We're talking about this too. U and W. U and W, I have some independent source from X. I have some independent source from X. So the two side, I don't know. But in the middle, I have a common cause of V. And so if I have a common cause of V, then U and W from independent, unconditional independent become uh, conditionally independent given V. So in other words, I need to take the piece out in order to make that happen. And finally, if you look at very, very far outside, X and Y, they are definitely not related, but I have a bunch of yada yada inside. The minute I have this middle piece of UVW storyline, a table built, and said that, okay, this table is influenced by Y and X. So X and Y are not conditionally independent of U and W. Or I can say that, okay, the minute I know U and W, or everything's in between, then now we're not independent anymore. We're related. And so computationally, a lot of time what we're trying to do is we would like to do uh, you know, summation, not multiplication, and we would like to find a small frame, and inside that small frame, we only need to do very simple computation and not the whole computations. Okay, and go online, you can find other table to discuss, but I think this one is a good one because you can just say that every time pick any three. Okay, you can pick U and Y. You can pick any three and say that, okay, uh, either we have a common parent or we have a common kid. And if we have a common parent or common kid, that make us from not related to related. Make sense? Okay.
For this, you'll be able to find the subsequent relationship between X and Y
Mm-hmm.
after doing all your computation.
Yes, yes. And why we're doing this is we're basically trying to say that de-separation is the way for us to decide how to build error. Okay, and when we try to build all kinds of errors, uh, for example, uh, well, we'll do that, but this is the example that I would like to. Okay, cause rain, cause wet grass, right? Probability, conditional probability, Bayesian rule, end of the story. Okay, next, common cause. Sprinkler and rain could be independent. But if I have a grass as a common cause to discuss this too, okay, they are dependent on my grass situation. And that's from the de-separation type uh, computational view. But at the same time, we're trying to build logics. Hey, this guy's is coughing. Could be cold, could be pneumonia, or cancer. And now both could have this, and could be a combination of the two. Cancer people still can catch cold. Mhm.
So wouldn't also rain or the sprinkler be dependent on rain? So a lack of rain, you subsequently have to use the sprinkler, and then you can find that
Aha. And so now, actually, you raised the question is that, but I have information about this, I have information about this, then what else? Or when you write your projects, a lot of time you said that, okay, there got to be something else I need to have to make this easier to understand. So now you get into, what if I know if it's cloudy? Because if I know it's cloudy or not cloudy, then there is an intelligent agent to decide if I should turn on the sprinkler or not. Because if it's cloudy enough, I think the likelihood to have rain is very, very high. And as such, the uh, the need to have the sprinkler on is low. So the causal is in your head, but what the logic we can, probability logics or deseparation logic we have is that sprinkler and rain are related based on a common parent and a common kid. Okay, and so then of course you can always say that, oh, I would like to add a little bit of, you know, if you have this, then you probably could also have this, or you have this, probably you will have something else. So what I'm saying is that uh, a lot of time you can have a diamond, and then on top of diamond, and got a branch coming in as an independent source, or a side effect as a, you know, a separate kit. And what's the beauty of doing that is a lot of time we can do our computation and said that, okay, if I know this and this, everything I need to know is gonna be carried in this node. So everything I need to know uh, summarized in D. I don't need to do anything anymore. Or vice versa, the other way around. Everything I need to know, if I know all the children's, that can make my life easy. And once you have that, then uh, you can just say that my study is really, where is my separation? Here we go. My study, my real interest is about UNW. But in order to understand UNW, I can have a sub-study here, a sub-study here, and then at the end, if UNW can be fully elaborated, I can forecast certain things that way. Uh, so the computation we need right now is still the mutual information, the probability table, and you can turn them into a, whenever you have a 2x2, 3x3, you can easily turn the probability table into a mutual information table for the KO divergence computations. But I would argue carefully with you on this, or negotiate with you on this. I know everybody is busy. At the end of the semester, you probably find some 5 to 7 columns of data. Do a tally, turn them into a table, and then throw them into some software, build some causal structure, and say, oh, model 1, model 2, model 3, KO divergence, very, very small. I find my winner, and then let ChatGPT argue with you, write some background story. How likely you get an A? Maybe. But I would say this. Uh, Try not to start from uh, the mechanics. I will always like to start with, what do you really care? Do you really care? Uh, you know, uh, why people not buying our hybrid? what kind of people buy our hybrid design? Is it because of the charging station? Are we using a very different charging connector? Or, basically have some logical myth or curiosity and said, in order to argue this, what kind of data should I have? And uh, how can I build my causal structure that way? I I personally think that you gain a lot more respect that way. Okay, um, and the other thing is that if you do that, uh, you've done some computation, but your computation not gonna be a lot. I know that you can have you can have several Excel spreadsheet or macro develop even, or using R. There are some R you can download to run those 2 by 2, 3 by 3 table, and done. And I'm at the end of once I have this built, I'm gonna introduce structure equation model because SAS can build a lot of structure equation, basically a bunch of regression for you to argue things. Okay, and what I'm trying to say is that uh, when you have too many complex computations, you're not gonna impress your boss. Your boss a lot of times, you've done a lot. Uh, but let me ask you this: do you like to watch a movie? But do you feel like modern movie with a lot of computer animation and a lot of battle simulation and imitation, and then of course a lot of time R-rated with sex and violence and everything? There, there are a lot of movies getting busier and busier, and the pace getting faster and faster. But you look at the box office record; they're not good. And then you argue or you look at this, and it basically said that at the end is the storyline is not well organized. It's just very very busy.
So, like, to your point, I think they're looking at like my generation. We have a very very short attention span,
Right.
and so they try and keep you intrigued throughout the movie with big
Mm-hmm.
explosions, gun battles, what have you. But that's only the surface of what we're looking. If you don't tie it in with like Forrest Gump has a fantastic storyline to it.
Mm-hmm.
If you don't tie everything together, then that's why it subsequently fails the box office.
Mm-hmm. And I would even say that you know, Lord of the Ring versus Harry Potter. Lord of the Ring, the sequel. Well, don't quote me on this, but they organize the movie, the storyline, and then get the whole things. And so all the technical stuff is to enhance the storyline, and usually people will appreciate that better. Harry Potter, the first three are pretty fun to watch, but after a while, you feel like, well, it's just another a flip. And TikTok the same way. Uh, 15 seconds, 1 minute, 2 minutes. After too many of those, you forgot what you actually see. Okay, so I would say this. Uh, what will impress me? 20 nodes Bayesian network for your projects, or you have a 7, 8 nodes, but you elaborate clearly. So why? So what? Who cares? And I probably say I prefer a better storylines. Okay, maybe does this class offer in computer science, or they probably just say that let's see who can write a code to handle you know big data. But my view is we're system engineer at the end. Our why we're using this is we try to ask why. I wonder why. And so what? Who cares? What can I do with this? Okay. For the two online students, I will say, your grad students, I will say this probably even more important is that I want you to demonstrate you can think and not just play with the mechanics. Okay. Now, having said that, let's do our mechanics. So the simple Bayesian net, not Bayesian net, just Bayes rule. Rain and wet grass. Rain is 4%, 40% of the time. So sunny or no rain is 60%. So given rain and grass is wet is 90, and given no rain and then grass is wet is 20. So far, 1, 2, 3. This is just like our signal detection theory. 3,000 engine, 50%, 5% are bad. Okay, and if you have bad engine, you will have some cranky noise. Now, you turn around and said that, but now if I have a cranky engine, I have a wet grass, okay, how likely, okay, I look out up the sky, I see rain, or I look up the sky, I see the reason. So now this is a Bayesian rule, right? Uh, R given W times PW equal to W times R given R. So far, so good. And then, so W really is the piecemeal of R or no R under those situations. And then on top of that is my W over R. And once you do that, and as the two different kind of causal structure, how likely to be in one of the causal structure. So there is a bundle, could be, there are bundle 1, there are bundle 2. And then how likely is my bundle 1? So bundle 1 over bundle 1 plus bundle 2, 75% of the time. So if the ground is wet, I look up the sky, I should see 75% of the time. Okay? So I'm just re-argue Bayes rule, but based on a de-separations points of view. Next. This time we have two worlds. Could be this, could be this. Okay? The baby, the kid is crying. How likely is yelled by mom or yelled by dad? I found most of American mom meaner than American dad. I'm on video. I hope this will be popular on YouTube. Okay, so we turn around. We said that there are 20% of the time sprinkler is on and 40% of the time rain is on. So we can just build this two causal structure independently. And then, of course, we'll start from this, right? If this is 2 by 2, this is 2 by 2. This is a table of rain, sprinkler, rain, no sprinkler, and or this 8 different conditions need to established, right? Yeah, basically why 8 conditions. Think about it this way, okay? Just ignore the whole things, right? You can build experimental design and said that I can have S, I can have R, I can have W. And then you just basically said that sprinkler is on is 0, and is not on is 0, and is on is 1. And then just do this, and then just do, oh, I got it right. No, yeah, I got it right. Technically speaking, a 2 by 2 by 2 A situation. And of course, don't argue with me. You can have 3 factorial, 4 factorial, then you just have -1, +1, or that different coding argument you need to go through. But if you have that table built, and then you just said that, okay, every time I just want to say that, okay, I want to know both 0, both 1, and 0, 1, 0, 1. So you will build turn this A table based on R is on, R is off, S is on, S is off, W is on, W is off. You can build this A conditional table, agree? Based on or everything you have. And then after that, some things. If S is on, the sprinkler is on, and it's wet, and sprinkler is on is wet, okay, and you basically say sprinkler is on, given there's rain, sprinkler is on, there's no rain, and those are the two sprinklers on situation, and then now you have SR and no R, and then you use the SR as no R, getting to this computation, and you will have the, because okay, here's the key part. I actually highlighted, I should ask you, why R given S and R no R given S become R and no R? You can tell. You here, let me go to equation editor. Oh boy. Hmm. Let's see if I can. You agree with me on this equation, agree?
So we can get rid of S because that is has the same R has the same dependency on S.
No. R and S, do they have common parent right now? So they are unconditionally independent. If I don't know anything about S, right? Anything about wet or not wet. So what I'm saying is that, or I'm asking you is, R given S equal to PR, because rain or no rain, so far we're not related. Rain or no rain, well, just keep this in mind, because very quickly we're going to argue. Now, if I know if it's cloudy or not cloudy, then see the table become this complex. Okay, so coming back here, but sprinkler or no sprinkler, sprinkler is on or sprinkler is not on, I rain or no rain, uh, equal to uh, just rain or no rain. Okay, so no rain or rain times PRWS, and you have this. So this whole thing is 0.92, and then you can play the same game of S given R and no S given R is just write PS and P given no S, because rain or no rain, so far there's no common cause. So this whole thing's become this. And so just by 0.01%, this is more likely, okay? Sprinkler on ground are more likely to be wet than rain the ground is wet, because sprinkler around is intentional, and that intentionality is 0.01%. So far, so good. Yeah. And now, okay. And if, okay, I turn around and now, just like the previous problem, I'm not interested in if this, then this. I'm interested in if the ground is wet. I look up the sky. Is it because of sprinkler or because of rain? So this is conditional probability. There's no flip, right? But this is flip. So how I flip is usually I know what happened. I wonder why. So it's PWS, PWS. And so this time still two independent source. PS is 0.2 and no S is 0.8 and R is 0.4 and no R is 0.6. And then you have this 2 by 2 by 2. So basically you can have this two, S and R re-summarize. You can add the probability together, because all you care about is this, right? Oh, I got this one wrong. This is my A conditions. So if I want to say what is the possibility of SNR, I can just summarize, combine this A table into this 4 table. No sprinkler, no rain, sprinkler and rain both down, and that will turn into uh, the table I have before. But what I really care about right now is that, okay, if I know that my rain or no rain, now I care about under those A conditions, those rain sprinkler, then I will have this probability. And intuitively, it's easy to see. If both rain and sprinkler happen at the same time, then 95% of the time the ground definitely gonna get wet. And if both no rain and no sprinkler and the ground is still wet, that's a miracle. So that's 0.1. And so now you can combine that and figure out the total probability of this this sprinkler, rain, no sprinkler, no rain combined together. This is 0.52, and you turn around and ask PW rain or PWSR. You basically said that, okay, totally I have this ground wet 52.52. How much is due to equation 1, this line equation, or this equation and this equation? So you just 0.076 divided by, you get this probability. So far, so good. So this is initial flip. And then after that, we just say that, okay, I only care about PW, ground is wet, how likely is due to sprinkler. And I'll have the PW 0.52, and then 2 out of the this 4 are due to uh, uh, I look up and I see sprinkler. Okay, no rain, rain. So I will have 0.352, and then I can have the other one is flip upside down, PW and R, and it's 0.7. So more likely I look up, I assume wet. It's due to rain, not due to sprinkler. Okay, and uh, I think I'm gonna stop. Well, let's see. Huh? Yeah, I know, I know. Let's see if we can. Yeah, let me finish this chart, and then we'll call it a day. Okay. uh, yeah. Okay. Yeah. Okay. And so far, this part is okay, right? And I would like to add one more. It's called explaining away. Is that if we can calculate the probability, ground is wet, uh, and I see the sprinkler, and uh, ground is wet and it's raining, how likely I see the sprinkler is on. And this is twist of the twist. That's why I would like to explain is how likely ground is wet, sprinkler is on. Okay, we have the ground is wet and sprinkler, ground is wet and rain and sprinkler is on. One more time, okay? I see rain, I see ground is wet, and how likely the sprinkler is on is 0.21 versus, okay, I see sprinkler uh, uh, is on versus ground is wet, okay, and then how likely is rain, okay, and I see that rain is more likely than this one, but also I can play this in a lot more detail way is, okay, if I know that it's been rain, okay, has been rain, decrease the probability the sprinkler is on. Would you agree with me? So now you see, even without getting into the common cause, flip, you can already create a lot of mind twisting example, and that's partially why I don't like the huge model. Huge model, you explain nothing well. I would rather you find a piece and say, I discovered this and I bet my life on it. Under this condition, that will happen. And usually you get uh, a lot more um, recognitions. I shared this story before. I don't know if I shared it with you. I probably share it in human factor class, the undergrad class. When I work for an insurance company, a lot of time we try to check how people fake workers' compensation and get, you know, extra money. And of course, if you go to a lot of emergency room, you see people in three-piece suit giving business cards out. Those are lawyers, and they try to say, "Oh, you hurt? Would you like to have workers' compensation? I can help you." And a lot of time, they even can have, people coach you, maybe in unintentionally, how to limp. So the PT or OT will say, "Oh, well, he hurt bad because he tried to move the fridge in the workplace or heavy equipment." And well, we have videotape showing that, and we show limping. And so we need to develop a lie detector to say if that's true, not true. And sometimes insurance company have legal department videotape uh, the someone filing a claim, but you videotape he play tennis in the afternoon, no problem. And the other thing we can do is a lot of time we know that if someone has pain, they have to guard their joints, so they will co-activate, say, their quadricep and hamstring, or their butt muscle, gluteus medius, in order to keep the joint stable and not getting hurt. And so when you limp, you will see that they file certain muscles, try to keep the joint tight. So far, so good. And so they fake well. And guess what? How we catch it, or I propose different method. We use EMG sensor, EMG electromyography, just like EKG or EEG. Just not listen to the heart. We listen to different skeletal muscle, and then we ask people, "Oh, walk forward. Now walk backward. Now walk sideways, left to right, right to left." Guess what? A lot of time we know how to fake our limb, guard the muscle, guard the joint, co-activate at this time. Probability wise, you have to do that in order to get it right. But we don't really have that kind of intelligence to say that, okay, now how should I fake this if I have to walk backward or sideways? So suddenly the probability of something shouldn't happen increase dramatically. So knowing you already got hurt, you're not supposed to, or you already have this problem, the likelihood to see the other thing should drop dramatically. And we can have a control group versus the actual group. And sometimes we just show the evidence, you know, to people and said that, well, how you explain this? They cannot explain because they, yeah. And so you can build lie detector. And banking industry and credit card company, they try to catch fault, all kinds of financial issues using the same tricks. Okay. Now, so here is the example. This time, we add one more common cause, cloudy, not cloudy, and then we'll have sprinkler on, and sprinkler is not on, and oh, here I didn't use 0 and 1, I use true and false, 0 and 1. It's F and T, okay, but it's the same thing. So you have a two grandparents table, you have the 2x2 parents table, and then you have a 2x4 kid table. So far, so good. And then after that, how to calculate uh, cloudy, ground is wet, versus uh, not cloudy, ground is wet. Okay, and we need to have two separated 4 conditions to get this 2 value and times the cloudy, not cloudy, 0.5, 0.5 to get this. So how to get to that point, break it down. This time, we just need to have PC or not PC 0.5, ignore that. Just on top of that, cloudy, rain, sprinkler on, rain, no sprinkler, rain, no sprinkler, no rain, and then times the conditional probability given that is wet. And here is the same things for those 4 conditions. And once you have that done, you just have that choo-choo train 1, choo-choo train 2, chain, 4 chain, get this one, chain, get 4 chain, you get the other one. And when you combine together, okay, you can basically argue, okay, if okay, if I have, well, if I have that whole table, I'll come back for the simulations later and validation later. Let's jump straight to that one. And basically now I can have the ground is wet, okay, but is it sprinkler sound? Ground is wet, if it's rain, flip the situation and figure out that, so it's more likely if ground is wet, it's due to rain, and you see that if it is more likely that the grass is wet because of the rain, because the likelihood is higher than the other one. Okay, and for all this, I'm not gonna give you homework immediately, but here's the homework. You don't need to turn it in. Okay, and please do this. Hide and solder table, you can fake one yourself, but just basically remember independent means multiplication. And then understand the D separation, formal language versus what I told you. I didn't say anything violate this more formal definition, but I would like you to visualize it and remember, or not remember, at least appreciate the more formal way of talking about it. Go through the separation of this branch coming back, and more importantly, the example of 1, 2, 3, all the way to this. All those slides I said today, build your own Excel table, and at least you know the answer, and you build a table, you can get whatever you want. Those templates can be very beneficial later on. You just change the number, you get the answer, and then you can build simple causal structure and use it again and again. And I'm not talking about for this class. I'm talking about when you deal with your boss and try to convince him, okay, this is the way to go in showing logic. All you need to do is change the name. Okay, let's have different charging station. Let's have different battery, and how likely our mileage, uh, uh, you know, our customer will be satisfaction will increase this much. You just need to have different name and different number. And what I'm trying to argue is that I don't care how complex the model you're going to have at the end. Usually you can escape a common cause, a common effect as your core to start with. Okay, yeah, this is the homework. You don't need to turn it in. You need it for your projects. You need it for a future. Build it, understand it, and you can use it again and again. Okay, and next time, let me finish this part, because if I done all this first, I can be very sloppy professor to argue, hey, now I give you all the tools good enough to start a project. But then, of course, I'll give you more efficient tools, especially some of the graphical representation and some other stuff that can make this life easier to dissect. And I was find time to explain the computational convenience. Okay, and this is important because I would say the opposite. This is important to impress people. What I found these days is that a lot of server computer, those large computer, they're really fast. Even what I'm saying is that if I use a very stupid branch and bound algorithm, I still get pretty decent answer than try to build a graph correctly in first shot. But you know, as a regular course, I cannot. I probably need to do some demonstration to show that, okay, here are the logic you need to be aware of. Okay, okay. You're the class representative. Visualize the whole things. Do you think you can connect the dots?
guess like your example of A, B, and C, trying to find like conditional independence. So like in that one case, it was A, B, and C were dependent on A. Your goal is to take A, find a relationship, but take A out of the equation to find the subsequent information gain
Mm-hmm.
efficiency.
Yeah. Here, actually, this sloppy game can even start even earlier. The play tennis or by computer. Can I have different credit score? I can have different age and different things. Can I turn them into a bunch of table? So probably I can have A, B, C, D, E, F. Once I have the A, B, C, D, E, F, let's just say F is my final buy or not buy. So lock that one. And then I'll just say that let me build a relationship, and can you easily build uh, naive Bayesian, everything related. Can you build your choo-choo train and said greedy, which one explain the best? And then after that, you can say that, okay, now let me just pick one cause, one effect. On top of that, rain and grass is wet is my first set. Who else I should pick to play this basketball pickup game? Pick one. The information gain should be high, and then it should help me explain how these things go. And then on top of that, let me have another one. Should I have that one, since I don't want to do naive, I don't want to do choo-choo train, should I put that one on top of, as my grandpa know, or should I have this know as a side effect know? And so you're basically doing this is kind of like we're revisit our who by computer, who not by computer, but just a little bit, a little bit, a little bit, and said, do I? Well, on one hand, you should have your. We're not doing it now. We should improve our KO divergence, right? Our information gain should get better and better. But at the same time, you just basically said that is this a converging or is this a diverging? And do I have this deseparation error, this directional error bell with some confidence? And yeah, if you can do that, basically you start writing your science fiction. Yeah.
So do you think starting with a general theory of so like your A, B, and C example,
Mm-hmm.
probability of A, B, and C. Let's say that that's my theory.
Mm-hmm.
And then subsequently, I need to be able to prove that with the individual relationships between A and B, A and C, B and C, things of that nature, so that I can try and see to prove my theory
Mm-hmm.
that A, B, and C have a relationship.
Mm-hmm. Or let's just say that uh, someone got COVID. Okay, what will be your first thought or first thing you would like to ask?
So they've already been diagnosed with COVID.
Well, just well they've been. Let's say that he visited the hospital. They give him a swab and then say, "Hey, you're positive," and swab a second time, double plus. You got it. What would be the first things they need to check?
I guess a one direct relationship would be white blood cell count.
Mm-hmm.
Then from there, you'd probably want to check your O2 levels, maybe your VO2 max, to determine do you have early onset pneumonia as a result
Okay.
of COVID.
So see, I like it because your way of thinking is about what is his current state. And so what can I, what should I do? And I probably but I'm so you're trying to figure out that so what, who cares part, which is good. You're building it from the effect side. My first thing that or current state side. First thing I would say, when did you take COVID shot? How many? 3, 4, 5? Like, I'm old, so whenever I want to travel international, the school just give me the warning. You don't you don't go until you have your shot. And the second things they should check is that, okay, you know, anybody in your house uh, got this, because more likely, if I have more than 5 shots or 6 shots, uh, where do you get this new strands of COVID from? Okay, anybody travel internationally, so they can trace and said that where this is coming from. And then, of course, they should check my medical history. Well, he's a strong guy, or he is not that strong, and how likely he can survive, and what will be the treatment plan, and branch out and do something about it. So we're we're, we're talking about this in layman term, but we're still trying to figure out that, okay, if something happened, okay, I should prevent that happen again, right? So you remember when you take the human factor, I said someone keep hitting you with a baseball bat, bang, bang, bang. What should you do? And when students said, "Oh, wearing a helmet or try to guard," I said that's wrong answer. How could you let someone hit you like that? So the first thing is get rid of the root cause. So your two part. Okay, there is a source. How to minimize that exposure and minimize that source, contain that source, quarantine that source from keep the things going. And then on the treatment side is what is the physical conditions, what is the level of disease, and then come up with uh, okay, Simon, sorry, we cannot do anything about it. Uh, you just need to quarantine yourself until you recover, or maybe here's a couple can release your fever or certain symptom. So I want you to argue your story not in a in layman term, and in a way that you feel it makes sense. Okay, I'm not saying you're wrong. Argue the current state of the problem. Argue where the root cause coming from, and can I do anything about it, or I just have to live with that uncertainty. And then on the potential outcome, anything I can do, or not going to make any difference. And so at the end, you don't want to tell your boss, or you don't want to tell the patient, I cannot do anything about it. You want to say, well, here are a few things, uh, either to help you or to help others from getting that. If you start thinking that way, you will figure out that among all the A, B, C, D, E, what kind of causal structure I would like to build in order to make that point. How many causal structure can you build if I give you some data? Tons. And so find a one that triggers some curiosity. Okay? Okay. I'm going to call it a day. And thank you for actually coming. I feel my foot hurt like crazy, but after I start teaching, it seems goes away.